Thank you. So let me start by thanking the organizers for their kind invitation. It's really a pleasure to be a part of this conference, and it's my first time in ICTS in this place over here. And I must say that I'm quite impressed with the way it is put up. Anyway, so I'm going to talk about the problem of bounding the size of L functions. Right? So let me start by stating the problem. So pi is an automorphic form for GLD. So I'll be just working over the number field of rational numbers. Okay, and we can associate with an L function, so that will be L is pi. Maybe I'll just define the completed L function. So the completed L function will be lambda s pi, so it's the product of the and the finite part. And I'll just remove this f over here. So that is going to be my the function of in my focus, where L infinity s pi is a product of gamma factors. So it looks like 1 by pi to the power s by 2, gamma of s minus alpha I by 2, where the number of terms in this product will be same as the d over here. Right? Right. And we know that it satisfies a functional equation. So lambda of 1 minus s pi, so there will be an epsilon factor, epsilon pi s, times lambda s pi tilde. This is the contragradient representation, where this epsilon pi s can be written as q pi to the power s minus 1/2 times epsilon pi, where epsilon pi doesn't depend on s anymore. So this q pi is going to be an integer. Okay. Right. All right. So the problem is estimate the size pi is the constant pi. Yeah. So it's 3.14 dot dot dot. Yeah. So estimate the size of the L function inside the critical strip, and that's more or less same thing as trying to estimate the size on the critical line. Okay. And for this, I'm trying to write down bounds for this one, and you have to so we have to define the scale. So what will be the scale? The scale is called analytic conductor. Okay, so it's defined as denoted by q pi t. It's the product of the integer q pi. It's called the arithmetic conductor times a product from iron from 1 to d, 1 plus this alpha i's, bring over there, minus it. Okay, so that's the definition of analytic conductor. Yeah, and then the Riemann hypothesis, of course, the Riemann hypothesis or the grand Riemann hypothesis will imply that this guy over here is bounded by, so the absolute value of this is bounded by q pi t to the power epsilon times some constant depending only on the epsilon, okay, for any epsilon positive. Okay, and this statement is called generalized Lindelof hypothesis, and it's a consequence of the generalized Riemann hypothesis. Right? Okay, so the usual notation for this is that we forget this, we don't mention this constant. We write that L half plus it pi is less q pi t to the power epsilon. Okay, sometimes we write that this constant, we write an epsilon here to mean that this implied constant depend upon the number epsilon. Anyway, so that's the Lindelof hypothesis, which seems to be as difficult as the Riemann hypothesis. And so the problem now is to say what will be the trivial estimate and whether we can break the trivial estimate in some cases. Okay? So the trivial estimate which is also called the convexity bound. And this follows from the functional equation plus a little bit of complex analysis. They together imply that L half plus IT pi is bounded by q pi t to the power 1/4. Okay. So that's the best you can say in general. Okay. This is the best one can say in general. Okay, so and the subconvexity problem is just trying to get an exponent over here, which is strictly smaller than 1/4. Okay, so that's called the subconvexity problem. (1/4 minus delta). Okay. In most applications, it doesn't matter what delta you get, as long as this delta is positive, you're fine. Okay. But if you have this Lindelof hypothesis in mind, then you really want to get delta as big as possible, and in one day you should aim at getting it 1/4. Right. Okay. So what do you know so far? Right. So the first subconvex bound. All right. So before that, maybe I'll just say that, yeah, there are three components hiding inside this definition of analytic conductor. One is this q pi over here, and that's called the arithmetic conductor, or I'll call it level. Okay. And the other, the spectral parameters, or the Langlands parameters, are kind of mixed up with the t part. All right. But in some cases, we'll be taking them separately. So if you fix the form, say the spectral parameter is fixed, then this product is growing like t to the power d. Okay? And if you take, for example, t equals to 0, then this product is like the product of the alpha i's. Okay? So this guy I'll denote by the norm of pi at infinity. Okay, so this is called the t part of the conductor. This is called the spectral part, and this q pi is the level part. Okay, and in some cases in subconvexity, you'd like to fix the two parameters and vary one of them. So in some cases, you'll fix the form, so the level and the spectral parameters are fixed. Then you're taking t goes to infinity. Okay, and then you try to get something less than t to the power d by 4. Okay, and that will be subconvexity bound in the t aspect. And sometimes your t is fixed, so you're looking at a fixed point, and you're varying the form. You can keep the level of the form fixed and vary the spectral parameter, and that then this part will be varying, and the subconvexity in that case will be called the spectral aspect subconvexity. Or you make the level go to infinity. Okay, so there are three different ways, three different parts inside this analytic conductor. So let me start with what are called the t aspect subconvexity bound. So this has a long history. It goes back to Hermann Weyl and Hardy and Littlewood. So this is a part of classical analytic number theory. Goes back to 1920s. And the bound they obtained was for the Riemann zeta function. Zeta half plus IT is bounded by, so a trivial bound, because it's of degree 1, it will be t to the power 1/4, but they showed that it's t to the power 1/6 plus epsilon. Right? And the same bound can be proved for Dirichlet functions also. So if your character chi is fixed, then this is bounded by t to the power 1 6 plus epsilon. Okay, so in the last 100 years, we have improved this to t to the power 1 6 minus 1 by 84 plus epsilon. That's kind of the current state of technology. In the case of d equals to, this is d equals to 1. So for d equals to 2, it was done by Anton Good. That was in 1980. And he proved the bound that, so he took F to be an SL to Z modular form. He showed that L half plus IT F is bounded by, so in this case, t to the power 1 half is the convexity bound, and he proved it's t to the power 1/3 plus epsilon. And since this is like square of zeta, right? So this bound is like the analog of the Weil bound. Okay? So this is also called the Weil bound. Of course, now it's known for any GL2 form. Okay, so known for. It was done by Muirman afterwards. Anyway, so that's for degree 2. For degree 3, we had to wait for some time. And this was done in 2015. So if I is an SL3Z form, then L half plus IT phi. So in this case, t to the power 3 is the conductor, t to the power 3/4 will be the convexity, and we have 1 by 16 plus epsilon. So this is not as powerful as the Weil bound, but nevertheless it's a subconvex bound, right? All right, so now for d greater than or equal to 4, this is more or less open. Okay, whatever method we have so far doesn't really work for d greater than or equal to 4. But in special cases, one can do something. So if you look at L half plus IT, pi 1 cross pi 2, when it's a Rankin-Selberg convolution of two GL2 forms, then you can show that this is bounded by, so again, you have Weil bound here. So maybe I'll just say, we know, yeah, I'm not sure whether we know a Weil bound here. So let me just use that. We know a subconvex bound. So t to the power 1 will be convexity. And this follows from the work of Michel and Venketesh from 2010. So apparently, no one wrote it down before them. Okay, so that's and also, yeah, that's all. All right, so that's more or less what we know about in T aspect. The next thing is spectral aspect. And in this case, for t equals to 2, it was done around 1980s by Vanage. So in his case, he took F to be modular form of weight k for say SL to Z, and he showed that L half plus I half F, so T I'm taking to be 0, is bounded by, so k square is the conductor here, so square root of k is convexity, he got some saving, so delta, for some delta. Okay, so this is a spectral, so you can work this out even for mass forms and in the spectral aspect, also known now. All right, so for the d equals to 3, it's the general, in general it's not known, but there is a recent work from 2017 by Valentin Blomer and Jack Butkin, who showed that, so in case of GL3, there will be 3 Langlands parameters, alpha 1, alpha 2, alpha 3, which add up to 0. So you have alpha 1, alpha 2, alpha 3, adding up to 0. And if you put some conditions, so you want them to be in the generic position. So you want, say, so all of them are going to infinity. So you want so alpha 1, alpha 2, alpha 3 are all of size capital T. And you also want their distance to be also quite large. So say they're bounded below by some epsilon times T. Okay? So they're in the generic position away from the boundary of the Weil chamber. And in this case, they could prove a subconvex bound. So in T to the power 3/4 minus delta for some delta. So again, for d greater than equal to 4, not much is known, but in special cases we can say something. So for example, for GL2 cross GL2, the spectral aspect was done first by Sarnak. That was in 2001. Really. And in the case of GL2 cross GL3, where so you're taking a GL2 form, say pi 1 times cross pi 2, where pi 2 you take as a symmetric square of a pi 3, where pi 3 is GL2, right? And you fix the pi 2 part. Okay, so this is fixed. And you take the spectral parameters of the pi 1 or GL2 part to infinity, then the subconvexity is known, and that's due to Shaoqing Li from 2010. And also in the case of GL2 cross GL2 cross GL2, where you keep 2 of them fixed and take the spectral parameter of one of them towards infinity, then also you know subconvexity. This is due to Bernstein and Reznikov. Okay, so that's what we know so far in the spectral aspect. Okay, and now let's look at the level aspect, which is a more arithmetic problem here. So the first case for d equals to 1, so when you have Dirichlet L function, so you take chi to be primitive modulo, say m, then L half chi is bounded by m to the power, so 1/4 is the convexity minus 1/16 plus epsilon. This is the well-known bound of Burgess from 1960s. Okay. So now this has been generalized for d equals to 2. So for chi modulo m, so if you look at L half, say, so first case is when you twist a form, a fixed form by chi. Okay, so f is fixed over here. So this is one way of generalizing this. Then we know subconvexity. So this, so here also it's m square is the conductor, and we know something comparable to Burgess here. Okay, so it was first done with a weaker exponent over here. It was first done by Duke, Friedlander, Advantage. But the Burgess exponent was achieved much later. So the first done by Duke, Lander, Ivanich. And also they worked out the general case where instead of twisting by chi, you can take f of level m, say, then the convexity bound is m to the power 1/4, and they could, one now has m to the power 1/4 minus 1 by 1,889 epsilon. Okay, so that, so basically Dipendra and Ivanich were the first to break the convexity, but they had a worse exponent, and the exponent was improved later by Michel and Blomer and Harkos. All right, for d equals to 3. So again, if you look at the twist, so pi is a SL3 Z form. So if you twist by chi, then this is the conductor is m cubed, and m to the power 3/4 minus some delta is known for. You can write delta down, and you can get something good here also. And again, for d greater than or equal to 4, more or less open, except in the case, in the two cases, one is GL2 cross GL2, other is GL2 cross GL2 cross GL2. So in this case, if you fix one of the component and vary the other, we know subconvexity. And in this case, if you fix two components and vary the other, we know subconvexity. Okay, this is due to Venketesh. And this is due to Michel and others. All right, so that's more or less all that is known so far in here. Yeah, one of them is fixed. So this is fixed, and this is varying. Yeah. This one? No, yes, so far no. Yeah. Okay, so that's basically the history of subconvexity in a nutshell. And the methods that people have applied so far is, of course, first the moment method. Sometimes with amplification. Okay, so here, if you want to get a bound for LS pi, you put pi, you embed it in a family, and then compute the moment over that family. And once you have an estimate for the moment, you get an estimate for the individual function. Okay, so that's basically the moment method. The drawback in that method is how to get a natural family. So you have to get a family which is not too big, because you want the individual contribution to be significant, not, and you also want the family to be big enough so that you have a trace formula type of thing. Okay, so that's the main problem. And from d greater than or equal to 3, it's not really known what family to work with. Okay, so the moment method doesn't really work for degree greater than or equal to 3. So there is a period approach. So period with some ergodic theory. This was introduced by Bernstein, Reznikov, and again by Michel Venketesh. And therefore, Michel Venketesh worked out the general GL2 cross GL2L functions where all the parameters were allowed to vary. So yeah, so that will cover where both of them are varying, I think, or maybe not. They still fix one of them. And the third approach is separation of oscillation. So which I'll describe in a moment. And the new theorem that I want to mention is when you take, so say pi 1, or maybe in my notation, so F is a GL2 form. Okay, so it can be a modular form or mass form, and pi a GL3 form. So look at L half, half plus IT, the Rankin-Selberg convolution of F cross pi. Then the convexity is, so T appears in the 6 count factors, so T to the power 6 by 4, so T to the power 3 by 2 is the convexity, and the bound that one can prove is that minus 1 by 42 plus epsilon for any epsilon positive. Okay? Okay, so I'll write down the proof of that result in a moment. But the same technique can be used to prove much more in that same setup. Okay, so this was done by my students and postdocs at ISI. So the people involved are Saurav Kumar Singh, Sumit Kumar, Prahlad Kumar Sharma, and Malesham. Okay, so this is the ISI gang, and they're proving the following things. So it's there. They have worked out the details. They're just writing it down now. Okay, so the theorem. So there are 3 theorems. The first is, So F and pi are fixed here. So F is again GL2, pi is GL3. L half F cross pi cross chi. So we have subconvexity in this case. So chi is modulo m. So m to the power 6 is a convexity minus delta for some delta positive. And again, if so you can so if not fixed now, say of maybe I'll just say the wet part, so wet k modular form for SL to Z, and pi is a fixed GL3 form. So L half F cross pi is bounded by, so now k appears in 6 places, so k to the power 6 is the 3 by 2 is the convexity, minus delta for some delta positive. And number 3, so here F is fixed and pi is varying, just like the way it was varying here in case of Blomer-Butkin. So they're varying and the spectral parameters are spread out. Here also you can get subconvexity. So here also, cross pi. So now it's, say, all of them are of size capital T, then it's T to the power 6 here, so it's again T to the power 3 by 2 minus delta. Right? Okay. Okay, so what is the advantage of studying the subconvexity problem for GL3 cross GL12 function? So right, so you can, so the method really works even if you pick one of them to be an Eisenstein series. Okay. So for example, if you pick both of them Eisenstein series, then LS F cross pi cross chi is basically LS chi to the power 6. Okay. And if you pick F to be an Eisenstein series, So maybe, yeah, take pick. So if is any form pi is the Eisenstein series, then so if so here both of them are Eisenstein. Here only pi is Eisenstein. Then LS, this guy is LS f cross pi cube, or you can pick f to be Eisenstein and pi to be a Cos form. Then this guy is going to be LS pi cross, sorry, so f cross chi, pi cross chi to the power 2. Okay. So that means if you prove these results, then almost all the results that I have written down over here will follow. Okay. For example, from this result, it's a result in T aspect. So if I pick one of them to be an Eisenstein series, I can get this. Of course, the exponent will not be as good as that. I'll get this one. Again, the exponent will be weaker than this. And I also get this one. So all of them in one go. Okay. And the first result over here, again, will give you this. Yeah, so it will give you this with a weaker exponent, and it will also give you this, and also will give you this with some exponent. And in the last case, you will get where's the spectral part? Yeah, you will get this, and also you get this. Where is the result? Yeah, and you will also get this, and not that. Yeah. So almost all the results can be proved this way. We are still making convexity, but the bound is not as good, and yeah, may not be as good as that. Okay. And the interesting part is the method is soft. So it's just some basic analytic number theory. Okay, so we'll apply the separation of oscillation technique, and this is how you do it. So step 1, so this sketch of the proof. So step 1. So the first step is, of course, to apply the functional equation to get an expression. Yeah. T is so T is right over here. So alpha 1, alpha 2, alpha 3 also is capital T. Yeah, so the step 1 will be to use a functional equation to write down the L value as a series. Okay, so the functional equation says that half plus IT f cross pi. To estimate this, we really need to estimate, so we can write it as bounded by some sums Sn by square root of n. And here you take the supremum over n going up to, so the conductor was t to the power 6. So n will go up to square root of the conductor, t to the power 3, plus epsilon. I'll have a small window over here, and an error term which is negligibly small, which gets better every year. Yeah, and Sn, where Sn here is a smooth sum. So now lambda Fn are the Fourier coefficients of f normalized, and denoted by lambda pi, maybe just, yeah, okay, lambda pi 1n are the Fourier coefficients of pi, and here n is of size capital N, right? Actually, it comes with a smooth weight, but I'm going to ignore the smooth weight. Okay, so now if you estimate this sum trivially, then you will see that you will recover the convexity bound. Okay, so to get a subconvex bound, you have to show that there is cancellation in such sums for n near square root of the conductor. Okay. So the problem is to show cancellation in Sn for n nearly of the size t to the power 3. Okay, so next step, so this is the separation of oscillation. So you look at the sum, there are two oscillatory sequence. One is lambda fn, other is lambda pi 1 by n. Okay, so individually you know that there is cancellation. If you don't have this, there is cancellation in this sum. If you don't have this, there is cancellation in this sum. The product, the problem is to show that the product also has a cancellation, right? So I'm going to separate them. So I'm going to introduce a new variable, m. Okay, but then it comes with an equation because n has to be equal to m for this to be equal to this. So that is denoted by delta nm. So this is the Kronecker symbol. Delta nm is 1 if n equals to m and 0 otherwise. And this is where analytic number theory kicks in. So analytic number theorists have revised over the last 100 years different ways of detecting events like this, when two things are equal and when they're not equal. Okay? And they are called circle methods. Step 3, we apply circle method. Is some form of circle method. All right. So, so before that, I have to do a little bit more over here. Otherwise, you don't get the result that you want. So the little more over here is we throw in an integral. So nm to the power iv, okay, where this v is of some size, a capital K. Okay, of course, when we have delta nm, that means n equals to m, this is just 1, and then the size of the integral is just k. So you have to divide by k over here, and you still have the equality. Right? So what it does is that if you just drop this condition that n equals to m, this integral still holds n and m quite close to each other. If n and m are quite far away, then this integral is negligibly small. Okay, it's a smooth integral. So what it does is it says that this integral is negligibly small if the distance between n and m, so they're generically of size capital N. So if they are greater than n by k, then it is negligibly small. Okay, so this integral holds these two variables close together at the loss of this equation n equals to m. Right? So that's the conductor lowering thing. Okay, so then we apply the circle method. Okay, so the circle method says that so delta nm is equal to 1 by q square a modulo q co-prime with q e of a n minus m q times some weight come over here, this is some analytic weight. Weight function. Okay. And this expression is there for any choice of q. Okay, so whenever you have to detect n equals to m, you can pick any q. It's up to you to choose, and you have this expansion. Okay, so I'm not writing down h explicitly, but you can write it down explicitly. Okay, but the thing is that when you have an equation of this form, where n is of size capital N, m is of size capital N, then you pick your q to be square root of the size of the equation. That's the optimal choice. Optimal in the sense that if you pick Q to be of that size, then you can ignore the weight function. Okay? So to ignore the weight function, we pick Q to be square root of the size of equation. Okay, so now what is the size of the equation in this case? So if you didn't have this integral, then n and m are both of size capital N, and the size of the equation will be capital N. Okay, so without this, it will be square root of capital N. But since we have put this in, so which says that n minus m cannot be larger than n by k, so the q will be slightly smaller. It will be this. So if you pick q to be square root of n by k, then you can more or less forget about the analytic weight function over here. Okay, so now we have separated the oscillations completely. Yes, so if you say that Sn, maybe I can write over here, Sn is now 1 by k q square. There is an integral over v of size capital K. There is a sum over q, size capital Q, a modulo q star. And then you have this sum over n, lambda fn. Oh, I forgot the n to the power it completely. So this is in the t aspect, right? So you have an n to the power it. And the n to the power it will be with this guy. All right, so we'll have an n to the power it over here. Sorry. So n to the power I t plus v e of an by q and then there is a sum over m of size n lambda pi 1m m to the power minus iv e to the power minus am over q. Okay, so that's what Sn is at the moment. Now you'll see that I have completely separated the oscillation. Okay, so there is nothing inside this n here. Some is involved over here. So n is not involved over here. M is not involved over there. So they are completely separated. And so if you now estimate this sum trivially, then what do you get? So if I estimate this trivially, this is like capital N. There are n many terms. Here we have n many terms. So that's n square. Here I have q many terms, q more, so q square, and k is the size of the integral. So kq square, but that's balanced by kq square in the denominator. So trivially, this is bounded by n square. But you want to show that this is bounded by something smaller than n. You want to show that it's bounded by n to the power 1 minus delta, right? So the problem here is to save. Okay, so this is the language we use in analytic number theory. So to save n to the power 1 plus delta. Okay. Now, so what are the things that we can do? So we can apply Voronoi summation formula. So we have we can apply GL2 Voronoi summation formula over here. We can apply the GL3 Voronoi summation over here, right? So apply GL2 Voronoi summation formula. And after applying the summation formula, you have to clean up a few things, but this is basically what you get. So we'll get a sum over n again, but now the length of the sum will be the conductor of this sum divided by the initial length. What is the conductor? So the conductor will involve q and t. So you can think of it, so if you want to find the conductor, this is the same thing as the conductor of L of it if twisted by some character modulo q. Okay, so this L function is related to this one. So if I change the additive character to multiplicative character, then you get something like this. So the conductor will be T squared times Q square. Right? So we get here TQ square by the initial length. And this is what's going to happen to the remaining things, A bar n by Q, and then there will be some integral. So this is the Hankel transform. Okay? Okay, so now, so if I, as I said, if I estimate this trivially, I get n. If I estimate this trivially, I'll get TQ square by n, but there will be some weight factor coming up over here, right? So the saving, in this process is basically given by the initial length, square root of the initial length by the final length. Okay? So that's more, that's basically n by TQ. Okay? So that really means that if I throw in the factors over here, estimate the Hankel transform, and then evaluate the sum trivially, my estimate over here will be n divided by the saving. So it should be TQ trivially estimated. Okay, so that's my saving over here. All right, now I apply the Voronoi summation formula, the GL3 Voronoi summation formula to this other sum. And again, this will give me a sum over M. But again, the length of the sum will be the conductor by the initial length. So now here it's Q and V, they are involved. Both will get cubed. Right? So it will be K Q to the power 3 by N. Right? You get lambda pi M1. And this additive character will now change into Klosterman sum. Okay, and then some integral will come. Okay, so that's the structure when applied to GL3 Voronoi summation formula gives you Klosterman sum. Right? And the saving here now, using the same recipe, initial length by the final length, square root of the initial length by the final length, will give you n by kq to the power 3 by 2. Okay? Okay, so that was my step 4. Apply Voronoi summation formula. And the step 5 is the magic. So this is something that happens. That's what. Okay, so now I will execute the sum over A. Okay, so I have here E of minus A bar n by Q, and I have over here the Klosterman sum. Okay, so you open the Klosterman sum, alpha minus n Q. And for the moment, forget about the star, and then here you have a complete additive sum. So this is 0 unless alpha is equal to n modulo Q, right? So this is basically Q times, so alpha gets determined. So alpha is n, so you get m n bar Q. Okay, so what's nice about this, you can evaluate the character sum precisely, and with respect to m, it's an additive character. Okay, and that's what plays the main role over here. Okay, so we have saved something when you executed the A sum. So the saving here. So if you evaluate this trivially, so this was Q times square root of Q. So Q to the power 3 by 2. It's Q over here, so you have saved Q to the power 1/2. Right? So if we put them together, we have saved n by TQ and n by KQ to the power 3 by 2 and square root of Q. Okay, so what is this? This is n square by t q square, and q square is n by k. So, sorry, I have to. And also, when you do the integral over v, then you get square root of k saving. Okay, so there's a square root of k saving over here. Yeah. So that is the k. So k to the power 3 by 2 root k. And so if you plug that in, you'll get n by t. Okay? So your job was to save n. You have saved n by t. So it remains to save t, which is quite big. Okay? But the sum was quite big at the start. It was size t to the power 3. Okay, so at this point, we have more or less done whatever was possible to do. But now the structure is quite nice, because now what we have is lambda fn, lambda pi m1, and here we just have m n bar q, and some bunch of integrals over here, right? And we have here three sums. So one is the size of q of size capital Q, n of size where is n? N is of size tq square by n, and m is of size kq cubed by n. Right? Okay, so now the Fourier coefficients have played their role, so now it's the time to throw them away. So one way to throw them away is to apply Cauchy inequality. So you apply the Cauchy inequality, okay, put the GL3 sum outside. The GL3 sum was it was m kq cubed by n. And throw the n sum inside and the q sum inside. Okay, so the GL3 Fourier coefficient is over here. You are doing Cauchy, so you need Ramanujan and average, which is there. Okay, so here you'll have lambda fn and e of m n bar q times some integral over here. Okay, so before Cauchy, we wanted to save t. So at this point in this sum, we need to save square, because Cauchy, when you go back, you'll lose the square of the saving, square root of. Okay, so now you open the absolute value square and apply Poisson summation with respect to m. Right? So when you open the absolute value square, you get two copies of n, n1, n2. You get two copies of q, q1, q2. Right? Lambda f n1, lambda f n2 bar, and then you get a sum over m of size kq cube by n, and here you have m n1 bar by q1 minus n2 bar by q2 times some integral. Okay, so now I apply Poisson summation. The GL3 Fourier coefficients are gone, so apply Poisson. So that this was step 5. And this is step 6. So when you apply Poisson, so how much you save? Yeah. So the saving, so you cannot save more than what you have inside this absolute value square. So the maximum you can save, so the diagonal is fine if tq square by n times q which is, so this is t square by n, and q cube is n to the power 3 by 2 by k to the power 3 by 2, should be larger than t square. And this happens if and only if k to the power 3 by 2 is larger than, is smaller than square root of n. So n was like t to the power 3, so it's like t to the power 3 by 2. So you need k to be less than t. Okay, so the diagonal contribution will be fine if you get k less than t. And if you look at the off diagonal, so the saving in the off diagonal is the length of the sum by n. But as I said, that it's the initial length by the final length square root, but that is not always true. Okay, and it's not always true in this special case when you have additive character. Because when you do Poisson on additive character, you get an equation, you save the whole thing, and not just square root. Okay? So the saving will be, you don't lose anything in the conductor, additive conductor, you lose square root of k because of the integral. Here, m is oscillating like m to the power iv, which is like k. Right? So this is like k to the power 3 by 2 by n, and again q cube is n to the power 3 by 2, sorry, k to the power, how much is it? 5 by 2 by n, and this is n to the power 3 by 2 by k to the power 3 by 2. So it's k times square root of n, which is k times t to the power 3 by 2, and this has to be larger than t square, and this can happen if you take k to be larger than square root of t, right? So if I take k to be larger than square root of t and less than t, I will be saving enough in the off diagonal and the diagonal, and that will mean I will be saving more than n. That's what was required to save here, and so I'll be able to break convexity. Okay, so that's it. So you get the subconvex bound. Of course, k will be chosen optimally. If you want to get a good exponent, pick k optimally, and the same thing works for the other theorem also. The same recipe. Stop with that. Thanks.